Since the beginning of modern science, there has been a dream of creating a unifying theory of all physical phenomena. We could think of it as a formula that we could write on the palm of our hands and which would correctly describe all the observable physical phenomena. For quite some time, such a formula seemed attainable because science was progressively unifying different phenomena into a single theory. For example, Isaac Newton unified the phenomena of celestial and terrestrial motion into a single theory. James Clerk Maxwell then unified the phenomena of electricity and magnetism into a single theory of electromagnetism. Ludwig Boltzmann then unified the theories of heat and mechanics into a mechanical theory of heat. Quantum mechanics then unified the theories of matter and light into a single theory of quantum particles. General relativity then brought together theories of gravitation and light. At every such step, it seemed that science is moving toward a theory where all phenomena would be unified into a single theory. Such a dream, however, has remained stagnant for the past century. By the 1920s, more than a century ago, all the main theories we use today to understand matter were available, and the attempts to unify them had already begun. After a century, however, all these efforts lie in shambles. In this video, we will talk about all these efforts at theory unification and why they have failed in a simple, intuitive manner. Toward the end, we will talk about why these attempts have failed and where the answer to unification lies. We will discuss the semantic alternative of matter and how it helps us understand why theory unification is a failed dream that will never be realized. Let's begin with the attempt to unify quantum mechanics and general relativity. This is sometimes called the quantum gravity problem because gravity is still not quantized. The quantum measurement problem is a separate issue in quantum theory that also hasn't been solved. But there have been hopes that either gravity will help solve the quantum problem, or at least by quantizing gravity, we will reduce the known theories into one less theory. The fundamental problem inhibiting this unity is that gravity is a theory of space and time curvature, and if we quantize gravity, then we must quantize space and time. A quantized space and time will be discrete rather than continuous. Calculus depends on continuity of space and time. Without that continuity, calculus cannot exist. Hence, discretizing space and time means throwing away calculus, which means undermining the primary mathematical model for all of science. This problem is solvable only by realizing that space and time in modern science refer not to an objective reality out there, but to each observer's senses. Relativity theory relativized measuring instruments quite like each observer's senses are relativized to those observers. Therefore, the continuity of space and time refers to the continuity of senses, and the discreteness of quantum objects refers to the discreteness of sense objects. The senses are continuous and the sense objects are discrete. The senses are the space and time, but the sense objects are entities within that space and time. However, if we look at one observer's senses from the perspective of other observers, then senses are also discrete entities. From each observer's perspective, space and time are continuous and infinite. But from the perspective of other observers, each observer's senses are discrete and finite. Hence, space and time are both discrete and continuous, finite and infinite. Similarly, there are infinite such spaces and times. How the same material reality constructs objects, space, and time is then the crux of the problem. Let's go through this problem and later on we will discuss how matter creates both senses and sense objects. If we recall from our previous discussion about relativity, then Einstein was trying to get rid of metaphysical concepts of space and time and reduce them to physical instruments such as a meter and a clock. The word space had no meaning other than the distance measured by a meter, and the word time had no meaning other than the duration measured by a clock. Once we convert space and time to material objects, then we know that they are not independent of material forces. A meter can be elongated, compressed, curved, or straightened due to the effect of other material objects. Similarly, a clock can be elongated, compressed, curved, or straightened due to the effect of other material objects. By this, space and time, or distance and duration, lose their universal objective meanings. Rather, each meter and clock becomes a different space and time. Therefore, relativity meant the loss of universality of space and time. The material instruments used to make measurements are the counterparts of our senses. At the dawn of empiricism, the use of material instruments was justified over the use of human senses because the human senses had variability while the instruments were supposed to be invariant. However, relativity showed that instruments are not invariant. Just like material senses are different for each observer, similarly meters and clocks were different for each observer. Thus, the rationale for saying that instrument measurements are better than human senses was gone when the instruments did not remain invariant. Rather, we could now say that the measuring instruments are just like the human senses because both are different for different observers. This point is further affirmed in the semantic view as we have discussed earlier. Therein, we talked about how a world is projected outwardly from the observer, but that projection is not reality. General relativity took a similar stance when it said that space and time are measuring instruments, which are just like the senses, and because they replace the words space and time in physics, therefore the world we see is a private world contained within the space and time defined by the measuring instruments called the meter and the clock. The idea that the world is projected outwardly from the senses is therefore not a strange or archaic philosophical view. It is rather the only sustainable view under the theories of special and general relativity. The real world goes out of the window in relativity because everybody's space and time is private and personal and at variance from other spaces and times. Therefore, everyone is carrying a personal picture of reality that is not shared with other observers, since they are observing with their senses or instruments, which are different from the senses or instruments of other observers. Einstein claimed that the real world cannot be known because all relativistic frames are equivalent. In previous videos, we refuted that idea and showed that all frames are not equivalent. Instead, even a moving observer can know that he is moving, although it requires the use of instruments other than meters and clocks. When the equivalence of frames is dropped, then we can talk about an absolute reality known by an observer which is not moving relative to any moving thing in the observable world. Thereby, we can say that relative perceptions are facts but not truths. They are facts because they are observed. They are not true because we can also know that our measuring instruments are being distorted by the observer's motion. Of course, relativity does not talk about that objective or absolute reality. But as we have discussed earlier, it lies behind the senses and it is projected outwardly. But the analysis of the problems of relativity just tells us that such a reality must exist. Thus, we come to the simple conclusion that space and time are the senses of the observer, and the relativized perceived world is within these senses. The senses are both discrete and continuous. If one observer looks at another observer, then he will see the other observer as one of the infinite things in the universe. Therefore, the observer's senses are not infinite, and yet, for each observer, their senses are the spaces and times within which the entire universe is contained. Therefore, an observer's senses are simultaneously infinite and finite, continuous and discrete. If we account for the fact that each sense sees things differently from the senses of other observers, then we can say that each sense is also a dimension or type of vision. Thus, we get the tripartite description of a sense, in which the sense is an infinite space, an infinite dimension, and a finite object. We also get a description in which the space is continuous, the dimension is continuous, and yet, as an object, the sense is discrete. We can never reconcile these three aspects of a sense in a physical worldview because the same thing cannot be both continuous and discrete, infinite and finite. But this paradoxical nature of the senses is accessible to everyone. The logical paradox doesn't make it impossible, it just makes it inconceivable. The next problem is that since perception by these senses are always discrete, if general relativity describes the measuring instruments or senses, and quantum mechanics describes the measured entities or sense objects, then there are two kinds of matter being described. One that is continuous, namely the senses, and the other that is discrete, namely the sense objects. Thus, in addition to the fact that the senses are both continuous and discrete, and they are both infinite and finite, we have the additional paradox that the senses are continuous and the sense objects are discrete, and the senses are infinite and the sense objects are finite. The same paradox that exists for the senses themselves exists between the senses and the sense objects. This paradox is the genesis of the quantum gravity problem, because if we quantize space and time, then it will be finite rather than infinite. If we quantize space and time, then it will be discrete rather than continuous. Quantization will make space and time consistent with quantum mechanics, but it will stop being space and time, namely continuous and infinite, which is how we think of space and time in classical physics. Since space is both continuous, discrete, infinite, and finite, therefore the paradox is unresolvable. But this paradox can be resolved if we think about senses rather than sense objects. Of course, we will have to treat the senses as concepts which are spaces, dimensions, and objects. That requires a reasoning system that cannot be accommodated within present set theory and logic. Hence, the problem of quantum gravity will never be solved within current set theory and logic. Whatever we call quantum objects are nothing but sense perceptions such as taste, touch, smell, sound, and sight. Similarly, whatever we call space and time is nothing but the senses within which the sense percepts are contained. Since the dawn of modern science, space and time have been ontologically separate from matter, which is supposed to exist within space and time. But in the theory of quantum gravity, space, time, and objects are ontologically mixed because both are treated as matter. The novelty is that space and time are also matter, just as the objects that were previously treated as matter. Thus, three categories, namely space, time, and object, become one category, namely objects. Thereby, the same thing is a space, a dimension, and an object. There is no mathematical construct for something that is simultaneously space, time, and object. Because since antiquity, Aristotelian logic rests upon saying that one thing is only one thing. One thing cannot be three things. But for the theory of quantum gravity, the same thing, that is matter, has to be three things, because space, time, and matter are now simply subdivisions within the category of matter. If we think about this problem from the perspective of calculus, then we realize that calculus rests upon continuous space and time because continuity and smoothness are necessary for derivatives such as dx by dt to be defined. If continuity and smoothness are broken, then no derivative can be defined, and that is the end of calculus. Without calculus, nothing else in science can work because calculus has been the enduring model of scientific description since the dawn of Newtonian mechanics. Even quantum mechanics uses calculus because it doesn't apply quantization to space and time. The Schrodinger's equation is written in a continuous space and time rather than a discrete space and time because calculus necessitates continuity and smoothness. Therefore, quantum gravity is not just a problem of quantum gravity. It is a problem about the use of calculus. When space and time are discrete, then the postulates of infinitesimals in calculus are false. There is indeed a smallest distance and smallest duration perceivable by an observer, because distance and duration are properties of the observer's senses. Human observers cannot perceive infinitesimals, and hence infinitesimals do not apply to human senses. No material instrument can measure infinitesimals. They are just hypotheses in mathematics. That hypothesis is refuted when space and time become the senses doing the observation. With the failure of calculus, all mathematical sciences using calculus become false. We will now turn to examining the issues of thermodynamics by itself. Once we understand these issues, then we will talk about the interaction of thermodynamics with general relativity and quantum mechanics. In each case, we will see a different type of contradiction, which makes their unity impossible, leaving us with contradictory theories that work in limited domains. We will finally connect this contradiction to Gödel's incompleteness, where no theory that uses numbers can be both consistent and complete. So let's look at thermodynamics now. The basic problem of science at the beginning of Newton's mechanics was that energy was given only two forms. One, a gravitational potential energy, and two, kinetic energy. As time passed, a few more forms of energy were inducted into science, although these descriptions of energy were not immediately unified. For example, with the introduction of thermodynamics, heat was recognized as yet another form of energy, different from kinetic energy and gravitational potential energy. Then, with the introduction of electricity into physics, a new type of energy called electrostatic energy was inducted. With the addition of magnetism, a magnetostatic energy was added. Finally, with the addition of electromagnetism, energy had four different forms, namely kinetic energy, gravitational potential energy, thermal energy, and electromagnetic energy. But all these forms of energy did not suffice to study matter even in classical physics. The serious problem was that while kinetic energy, gravitational potential energy, and electromagnetic energy were attributed to individual particles, The collections of these particles had numerous other properties which were not reducible to the properties of the particles. For example, we cannot reduce properties such as electrical conductivity, surface tension, or viscosity to the properties of the particles because the particles don't have these properties. Physics would call these emergent properties rather than fundamental properties. We could measure these emergent properties, but we could not explain how these emergent properties emerged from fundamental properties. This remained a problem for physics for quite some time. Then Ludwig Boltzmann clearly showed that thermodynamic phenomena, namely the properties of pressure and temperature, required us to violate the assumptions of classical physics. The basic assumption in classical physics was that each particle is in a definite state. Classical mechanics was also a reversible theory. However, thermal phenomena were irreversible. For example, kinetic energy could be partially, although not fully, converted to heat. Similarly, heat could be partially, although not fully, converted to kinetic energy. This means that if we converted kinetic energy to heat and then converted heat back to kinetic energy, the final kinetic energy would be less than the initial kinetic energy. To preserve the conservation of energy and yet account for this discrepancy of missing energy, Ludwig Boltzmann postulated that a classical system was not in a fixed state. Rather, it was in all the states simultaneously that it could be. The total number of possible states came to be known as the configurations of a system, which meant that we could reconfigure a system internally, but the effects of that reconfiguration would not be detectable for an observer. In so doing, Boltzmann created a new property called entropy, which was the logarithm of the total number of possible configurations denoted by omega. Boltzmann then showed that the irreversibility of thermal phenomena could be explained by the assumption that a system was in omega possible configurations simultaneously. Whereas the individual classical mechanical particles were always in a single state, a collection of such particles was simultaneously in all the possible configurations and states of these particles. When energy was in a single state, then it could be fully extracted from the system, and the system was reversible. But when energy was distributed in a very large number of states at once, then it could not be fully extracted, and the system became irreversible. Entropy is a much misunderstood concept because it is equated to disorder, but these two are different ideas. Suppose I give you the title of a book with a broad outline using which you can produce the book. In this case, you can say that the title and the outline of the book could be satisfied by millions of different books that reshuffle the words, sentences, paragraphs, sections, and chapters, although they produce the same result, namely the book. Therefore, given a title and a summary, what is really a book? Is it one of the precisely articulated books, or is it all the possible books with the same meaning that could be articulated? The answer is that if we just have the book title and outline, then knowing that much is equivalent to not knowing which one of the millions of possible books we have at hand. Now imagine that I give you titles and outlines of two thin books and just say that they could be merged into a single fat book. Obviously, the total number of possible fat books that will carry the same information as the two thin books will dramatically increase because the information in the two thin books can be presented through millions of fat books. Now, if we have a fat book, then can we separate them back into thin books? Yes, that is also possible. Just as thin books could be merged into a fat book, similarly, a fat book can be separated into thin books. But both merger and separation have to be done slowly. If we tear the pages of the book and mix the pages, then we can get a fat book, but it won't be equal to the thin books. Likewise, if we tear the book into its pages, then it won't be two books, it will just be pages. Hence, when natural processes are done slowly, then they are reversible. But when they are done quickly, then they become irreversible. We can use this example to understand thermodynamics. When Boltzmann says that the system is in all the possible states, he means that a system summarized in terms of a few variables like temperature, pressure, volume, and so on is like the title of a book with a brief summary. We know so little about the system that it is as good as just knowing the title of the book and not knowing the precisely articulated book. Then, when he says that entropy grows and disorder grows with it, he is talking about a fast process in which books are torn into pages, the pages are mixed up or separated, and the net result of tearing the book and mixing up the pages always grows the entropy or disorder. But if the process is done slowly, then the process would also be reversible. Generally, in industrial systems such as an engine or a turbine, the processes are very fast. That is not so in nature, where the processes are very slow. Therefore, an industrial system produces disorder while nature doesn't produce disorder. This is because nature is doing the processes slowly while the industrial system is doing the processes very fast. The second law of thermodynamics states that entropy must not decrease, which means that disorder must continuously increase. This is contingent upon two factors. First, we have to treat a book like a jumble of words and pages. Second, we have to do the processes fast such that there isn't enough time to merge two books properly into a single book or to split a single fat book properly into two thin books. The condition of creating a book like jumble of words and pages is true for all classical mechanical procedures where a book has really no meaning and therefore it doesn't exist. The condition of mixing books and splitting books fast is true for industrial systems, relying on the classical mechanical procedures such that the semantic properties of the system are not allowed to play a role. Thus, the predictions of thermodynamics come true because we treat a book like a jumble of words and not allow it to organize itself into one larger semantic system, or split that book into two smaller semantic systems. Contrast this process with that occurring in an organism. An organism eats some food, and that food is slowly digested and it becomes part of the organism. The process of ingesting, digesting, and assimilating food takes many hours. This is an example of a slow process in which two systems are merged and they become one system. Similarly, when the organism eliminates waste, then one system splits into two systems such that the integrity of the two systems cannot be called creating disorder. It is rather the process of producing order and reducing entropy. Therefore, thermodynamics is not a law of nature. It is the law for mechanical systems being treated as non-semantic systems, akin to treating an organism as a collection of meaningless parts. We can compare that to treating a book as a collection of pieces of paper with no fixed order between them, and the whole system being measured in terms of physical properties rather than as units of meaning. This is also the result of running industrial processes at such a fast rate that the semantic or organismic properties of the system are not allowed to occur, and hence their effects are not realized. By the combination of mechanical thinking and industrial application of that thinking, the laws of thermodynamics seem true, although they are not true in general. The problems with thermodynamics become evident when we try to look at all the macroscopic properties of a system. Boltzmann was able to explain 2 out of a dozen or so properties of collections, namely temperature and pressure. But there are over a dozen properties that have no relationship to entropy. Therefore, thermodynamics became a subject about the study of heat, temperature, and pressure, but the study of the other dozen or so properties were still outside thermodynamics. These properties that were excluded from thermodynamics included properties such as surface tension, compressibility, capillarity, viscosity, malleability, ductility, and so on. These are properties of collections of particles, but they were not the properties of individual particles. They could also not be reduced to the properties of particles with the assumption that energy was being redistributed at once into many states. They were instead following their own curves of change. Thus, separate areas of physics were created to study these subjects. For example, the study of electrical conductivity became a study of materials rather than a part of thermodynamics. The study of melting and boiling points became a part of physical chemistry, and so on. The theory of thermodynamics and entropy worked for a few properties and not for the others. The natural cycles of food and waste illustrate the problem with entropy. When an animal eats food, the total entropy, that is, the total number of configurations possible, increases. But factually, the animal body isn't anywhere near the total number of possible configurations. The food is ingested, digested, and assimilated in a manner that the total number of configurations after eating the food is far lesser than the total number of possible configurations. This can be explained only when we treat food as a sequence of meaningful symbols in a sentence rather than as disjointed words. The total number of possible sentences is huge, but there is just one sentence in reality. Then, when the food is excreted as waste, the total number of possible sentences is still huge, but the actual sentence is just one. When that sentence is consumed by a plant, the sentence is broken into words and reorganized into new sentences. Even as the total number of possible sentences is huge, the actual sentences are very few. When the remaining words are excreted, they become food for the animals, which means that the words are again assembled into new sentences. Thus, we can speak about two tiers of semantic reality, namely words and sentences. A sentence is always order rather than disorder. However, every sentence is not perfectly meaningful to every organism. The organism breaks the sentences, creates new sentences, and rejects the remaining words as alternative sentences that are meaningful to other organisms. In this way, entropy is not created in life cycles because all the possible configurations of matter are not reality. There is just one configuration of matter out of a huge number of possible configurations. Life cycle processes also run very slowly in contrast to industrial processes that run very fast. If the food was eaten and excreted immediately, the processes of digestion and assimilation would not occur. In that case, there will be a net increase in disorder because the organism spends time to break the food but gains nothing from consuming the food, and what it excretes is not useful to the plants. The fast process is wasteful and the slow process is useful. When the processes are slowed down, then they become reversible and neither is entropy increased by this process, nor is there growth in disorder in nature. The fact is that nature has existed in a stable form for billions of years. It is only recently, due to industrialization, that nature is undergoing increased amounts of consumption and destruction. The waste produced by humans is not food for anything in nature. This means that waste keeps collecting and cannot be recycled by nature. That is net growth in entropy and disorder. Entropy increase therefore applies only to a physical treatment of matter, which is specially exacerbated when the process of consumption is rapid machine movements of industrial consumption and production. The presence of reversible processes in nature doesn't negate the possibility of irreversible processes. However, once we understand how semantics solves the problem of entropy, then we need to understand irreversible processes also in a new way. That new way, as we will shortly see, is quantum mechanics. The basic problem of semantics is that it often uses non-binary logic. For example, we can say that an elephant is both its tail and leg, but the inversion is not allowed because the tail and leg are not the elephant. This arises as a result of whole part thinking, in which when we move down an inverted tree, then we can say that root of the tree is also the trunks, branches, twigs and leaves, because all these things have come out of the root. But when we rise up the tree, then we cannot say that the leaves, twigs, branches and trunks are the root, because they are the effect of the root. This logic can flow from cause to effect, but not from effect to cause. In binary logical thinking, if an axiom leads to a conclusion, then we can also treat the conclusion as a new axiom and derive the old axiom as the conclusion of the new axiom. This is reversibility in logic. This reversibility also makes scientific theories reversible in the sense that if the time direction was inverted, then the effects can become causes and the causes can become effects. Irreversibility, on the other hand, tells us that we cannot invert the cause-effect relationship. What is axiom cannot become the conclusion, and what is conclusion cannot become the axiom. This non-binary logical treatment of semantics entails irreversibility, but it is driven by semantics rather than by entropy, which arises due to the absence of semantics. Quite like special and general relativity, where we rejected the axioms of Einstein and yet accepted the phenomena of time dilation, length contraction, and space-time curvature. Similarly, in case of thermodynamics, we can accept the observed phenomena of irreversibility without accepting the axioms of entropy, on the basis of which this irreversibility is explained by thermodynamics presently. As we discussed in an earlier video, there are two models of atomism, namely classical and quantum atomism. The classical atomism is like pieces of an apple, while quantum atomism is like the taste, touch, smell, shape, color, and size of the apple or the apple pieces. The classical atomism separates the pieces of the apple, but quantum atomism keeps the taste, smell, color, shape, etc. entangled. We can see the many faces distinctly without separating them from one another. In the earlier video, we also compared classical and quantum atomism to parts and faces, respectively. This was in the video on quantum collapse and entanglement. The parts can be removed without changing the other parts, but the faces cannot be removed like that. If one face is removed, then all the faces are changed. This was yet another simple way to understand quantum entanglement, as we discussed earlier. Now we can apply quantum mechanics to a thermodynamic system with over a dozen properties. The fact is that if we raise the temperature of such a system, all the properties of the system change at once. This is just like changing one phase changes the other phases as well. Every single property is altered because all these properties are mutually entangled. We cannot separate the melting point of something from its surface tension. These are not classical parts that can be removed from each other, and yet they are distinct and distinguishable properties. Hence, the macroscopic properties of a thermodynamic system have to be treated as various entangled quanta. A thermodynamic system also has to be modeled as a quantum rather than as a classical system. Current quantum theory models a quantum system as a reversible system, which makes it contradictory to thermodynamics. To understand how a quantum system can be irreversible, let's take the example of two tumblers half filled with liquid. When more liquid is poured into the first tumbler, after some time it overflows into the second tumbler. Then, when the liquid is removed from the first tumbler, the liquid from the second tumbler is not removed. This is an example of the kind of behavior that must be exhibited by a system for it to be called irreversible. We can describe irreversibility in everyday life through the analogy of trying to lose body fat. When we eat, the whole body gains fat. We don't have to separately put fat on all the body parts. All the body parts automatically get fat. But when we have to lose fat, we cannot just exercise one body part to lose fat in all the body parts. Exercising one body part doesn't drain fat from all the body parts. Therefore, we have to exercise all body parts to lose fat from all the parts. This is just like liquid goes from one tumbler to another easily, but removing it from the first tumbler doesn't remove it from the second tumbler. This problem is called hysteresis in thermodynamics. It basically means that some processes are easy in one direction but difficult in the reverse direction. Irreversibility is easy to understand in a semantic system, which is layered into many tiers of shallow and deep realities. The deep reality is the cause, and the shallow reality is the effect. When we gain weight in the beginning, the shallow reality puts on additional fat. But as time passes, this change passes into the deep reality. Once it has become a part of the deep reality, then it is very hard to lose weight even by exercising, because exercising just alters the shallow reality while the deep reality remains unchanged. To lose weight, we have to consistently exercise for a long time so as to change the deeper reality. The techniques for changing the deeper reality are different than for changing the shallower reality. At least, to change the deeper reality using the same technique, we have to apply the technique for a longer time. Some people lose weight easily because the deeper reality hasn't been affected by the weight gain. But once the deeper reality has been affected by the weight gain, then the weight gain becomes irreversible and much more effort is required to lose weight. Even if weight is temporarily lost at the shallow level, because the deeper level reality has not been changed, therefore, the moment a person becomes lax, he or she gains weight again. Current quantum theory cannot explain irreversibility because reality is not described in a hierarchical or tiered manner. If you remove a face or part, all the parts immediately change, which is reversible behavior. But imagine a scenario in which it was easy to entangle two systems but hard to disentangle them. Current quantum theory does not support such a system. Hence, quantum theory and thermodynamics are logically contradictory theories. We can see irreversible behaviors in reality, but we cannot explain those behaviors on the basis of quantum theory. Thus, when we take a semantic approach, then we accept irreversible phenomena while rejecting the entropic explanation of the irreversibility. In the entropic explanation, a system becomes irreversible because the total number of possible configurations of the systems grows. But in reality, even as the possible configurations may grow, the real configurations are not growing. In reality, the system is just in one configuration. Therefore, using possible configurations as a way to explain the reality is a baseless approach. The correct approach is that we accept that the system is in one configuration, but describe that configuration hierarchically as shallower and deeper realities. By this, we get irreversibility without using entropy. This is just like we earlier accepted the relativistic length contraction, time dilation, and space time curvature, while rejecting its explanation based on the equivalence of observers, and provided an alternative explanation based on the movement of consciousness. Thus, a theory is not necessarily true because it correctly predicts and explains some phenomena. It must explain all the phenomena correctly for it to be considered true. In this case, current quantum theory doesn't explain irreversibility, and thermodynamics doesn't explain entanglement. To explain both, we have to replace their axioms with a semantic view of reality. Factually, nothing is irreversible. It is only harder to reverse certain things. A reversible system is easily reversible. An irreversible system is harder to reverse. If a glass of milk has spilled on the floor, in principle we can put the spilled milk back into the glass. It is just harder to do that. Irreversible phenomena require non-binary logic in which not x is not equal to x, because not x was easily achieved, but the reversal of not x is very hard. For example, x can be milk in the glass, not x can be spilled milk, and reversing that spilled milk back into milk into the glass is harder. The irreversible processes require a deeper level of change. For example, we have to bring the glass to the floor and sharpen its edges so that we can put the spilled milk back into the glass. Thus, irreversibility is nothing but non-binary logic from cause to effect. The cause to effect is very easy, but the effect to cause is not easy. This is just like saying that the elephant is the leg, but the leg is not the elephant. The elephant is the deeper cause and the leg is the shallower effect. The cause can produce the effect easily, but it is harder for the effect to produce the cause. In earlier videos, we have discussed how the frame equivalence on relativity is a false idea because there are always ways to detect whether an observer is moving. We gave the simple example of a car running on a road previously. The driver can say that the road is moving backward rather than the car moving forward, but this claim can be refuted by observing the car's fuel tank and temperature. Therefore, when relativity is applied to thermodynamics, a contradiction is created in which some observer says that temperature is high and another observer says that the temperature is low. And the fact is that one of them is right and the other one is wrong. This contradiction then refutes the relativistic equivalence of all reference frames. The problem with the relativistic equivalence of observers can be illustrated easily by taking the example of two observers, one static and the other moving. To the static observer, the moving gas particles will indeed seem to be moving, and he will conclude that the temperature of the gas must be high. The moving observer, however, will find the moving particle static, and he will conclude that the temperature of the gas is low. According to relativity, if the moving observer touched the chamber of gas, he should not find it hot. But any observation will refute this claim. The moving observer will find the gas chamber hot just as much as a static observer. Therefore, their conclusion of the frame equivalence is refuted by measuring the temperature of the gas and finding it the same across the two observers. As we have discussed earlier, relativistic frame equivalence can be easily refuted by taking the example of a car moving on an empty road. While in theory an observer can say that the car could be static while the road could be moving backwards, in reality the moving car will have a higher temperature and will eventually run out of fuel. That will not happen in a static car. Therefore, the observer in the moving car cannot simply look at motion. He has to also look at the fuel tank getting empty and explain that fact along with the fact of observed backward movement of the ground. When both facts are put together, then relativistic equivalence is falsified. Another simple example is that of a person getting tired while traveling but not feeling tired otherwise. Similarly, when the car comes to a rest, we cannot say that it is equivalent to a car that has never run because the history of the car can be noticed by looking at the empty fuel tank, which was previously full and still remains full for a car that was always static. Some observations, such as that of length contraction and time dilation, have been reversed. But other observations, such as that of an empty fuel tank, may not have been reversed. The mass of a car at rest is also not the same as that of a car that has never run because the mass of the fuel is deducted from the car that has run, but not deducted from the car that has never run. Asserting frame equivalence is contradictory to thermodynamics because fuel burns out and the car as a whole loses mass. We can summarize all these problems in terms of contradictions between quantum mechanics, relativity, and thermodynamics. General relativity and thermodynamics are contradictory because all reference frames are not equivalent. The method that general relativity uses to explain length contraction, time dilation, and space-time curvature, namely the equivalence of all reference frames, is untenable in thermodynamics. Similarly, general relativity is a reversible theory in the sense that if we invert the direction of time, then all the equations will work just as before. But thermodynamics is not reversible. Again, the method that thermodynamics uses to explain irreversibility, namely entropy, is untenable in general relativity because the system is not in all possible configurations. It is only in one configuration. Similarly, there is a conflict between quantum mechanics and relativity, namely that space and time are continuous in relativity, but quantization requires space and time to be discrete. According to relativity, light spreads equally in all directions, but in quantum theory, light is occasionally transmitted as a photon in some directions. Finally, thermodynamics is contradictory to quantum mechanics because thermodynamics is irreversible while quantum mechanics is reversible. Similarly, quantum particles are entangled while particles in thermodynamics are independent. We can summarize all these problems through a simple graphic that shows how physics relies on three mutually contradictory theories that cannot be reconciled because each theory uses opposite assumptions or models opposite types of phenomena. It is reversible versus irreversible in the contrast between quantum mechanics and thermodynamics. It is relative versus absolute in the contrast between general relativity and thermodynamics. It is discrete versus continuous in the contrast between general relativity and quantum theory. It is entangled versus independent in the contrast between quantum theories and classical physics. Due to these contradictions between fundamental theories of physics, we can never expect to get a unified theory. As we talked at the beginning of this video, in the early days of science, there was continuous unification of phenomena into a single theory. There was a unified theory of celestial and terrestrial motion. There was unification of electricity and magnetism into a single theory. There was unification of the theories of light and matter in quantum mechanics. There was unification of the theories of light and gravitation in general relativity. Due to this continuous progress in science, there was a firm belief that as time passes, science will eventually come to a single unified theory. That dream, however, lies shattered today because no progress has been made on the fundamental issues of science. Now, most scientists will talk about the history of progress and say that they will eventually get a unified theory because unification was occurring in the past. But they will not say that science is riddled presently with contradictions, that we are torn between the two sides of dualisms, such as continuity versus discreteness, reversible versus irreversible, infinite versus finite, entangled versus independent, relative versus absolute, order versus disorder. These dualisms prevent any kind of unity. We need both sides of the dualism because some phenomena need one side of the duality, while other phenomena need the other side of duality. We cannot reconcile these dualisms in a logical system that abhors contradictions. And yet, without reconciling these dualisms, we will never have a unified theory. The problem at the moment is not experiment or theory, it is logic itself. It is logic because we need opposites, but we cannot reconcile these opposites. Therefore, a fundamental rethink has to be done ground up, including in terms of logical contradictions. At the beginning of this video series, we talked about Gödel's incompleteness and how it creates a fundamental tension between inconsistency and incompleteness in all logical systems that rely on mathematics. Most people think that the problem of Gödel's incompleteness is just an isolated issue about some mathematical theorems, although it is not. In this video, we have established how the same problem of incompleteness versus inconsistency appears in physics. There are three theories that we have talked about, namely quantum mechanics, general relativity, and thermodynamics, and we showed that each of these theories is contradictory to the other theories. Meanwhile, each individual theory is also incomplete because it doesn't explain the phenomena explained by the other theories. There are six fundamental dualisms in physics today, and physics is not capable of solving any of these dualisms. Each dualism produces a logical contradiction if we try to solve the dualism. Without the solution to the dualism, the theories remain incomplete. Hence, the problem of Gödel's incompleteness can also be stated as the problem of dualisms. Each side of the dualism works in some cases, but not in all the cases. The other side of the dualism is necessary in the other cases. But there is no way to integrate the two sides of the dualism within any current logical system. Therefore, the problem of Gödel's incompleteness is not an isolated issue about some mathematical theorems. It is the central issue of physics as well. We can repeat this process of studying the dualisms, subject after subject, and show that in every subject there are numerous dualisms. We need both sides of the duality and we cannot logically reconcile the dualism. Therefore, every subject exhibits the problem of Gödel's incompleteness, in that all theories are incomplete and trying to merge multiple theories leads to a contradiction. When we repeat this process subject after subject, then we realize that the problem is not that subject or even the mathematics. The problem is the logical impossibility of a dualism. Without a general method for solving dualisms, there can never be a unified theory of any subject. This problem is not seen in the beginning of a subject because a dualism is used for limited success in a theory. The problem appears over time when we realize that we have done everything we could do while living within a dualism. Further progress now requires us to go beyond the dualism, but logic will not allow us to do that. We have also talked about a semantic alternative in which each thing is three things. Each of these three things are just like the faces of one thing. If dualisms are applied to these faces, then we can reconcile the dualism without a contradiction. Here we can talk about three dualisms and how they are reconciled in Sankya philosophy. The senses are continuous, but the properties and their objects are discrete. The sense objects are absolute, but the senses and the sense properties are relative. The sense properties are reversible, but the senses and the sense objects are irreversible. The senses, sense properties, and sense objects are all matter, but they are not the same kind of matter. Some matter is like space, another matter is like dimension, and yet another matter is like an object. Everything can be treated in three ways because those three ways are the faces of the same thing. Each face uses a different dualism because the faces resolve the dualism collectively. Therefore, there is no logical contradiction. However, this is not Aristotelian logic either, in which one thing is only one thing. Aristotelian logic has no room for faces of a thing, let alone contradictory faces. Because when something has contradictory faces, then it becomes a self contradiction between the two faces of the same thing. Self contradiction is not permitted in logic. Non binary logic becomes essential because everything has contradictory faces. Just like a coin has two contradictory faces, namely head and tail, similarly logic has to become like a coin in which the same thing is two opposite things. The same thing can be discrete in one face and continuous in other face. The same thing can be reversible in one face and irreversible in another face. The same thing can be relative in one face and absolute in another face. The same thing can be finite in one face and infinite in another face. The same thing can be entangled in one face and independent in another face. The same thing can be ordered in one face and disordered in another face. Logic needs to shift from object thinking to aspect thinking. These aspects are very common with persons. The same person is sometimes kind and sometimes cruel. The same person is sometimes tough and sometimes soft. The same person is sometimes polite and sometimes harsh. The same person is sometimes independent and sometimes dependent. The same person is sometimes cool headed and sometimes hot headed. We cannot say that a person is just one side of the dualism. We cannot reconcile the opposite sides of dualism in binary logic. Therefore, non binary logic is also the logic that deals with persons instead of objects. Sankhya is the science of studying this faceted and aspected nature of reality. The three guna of Sankhya have infinite incarnations. But in one such incarnation, sattva is denoted by the senses, rajas is denoted by the sensed properties, and tamas is denoted by the sensed objects. Therefore, if we want to form a unified theory of senses, sensed properties, and sensed objects, then we need Sankhya. Otherwise, we can have separate theories, one for senses, another one for sensed properties, and another one for sensed objects, and they will be contradictory to each other and incomplete descriptions of all the phenomena because most of the phenomena involve the interaction of senses, sense properties, and sensed objects. Separation of senses, sensed properties, and sensed objects is an anomaly of modern science rather than the thumb rule for nature. Nature is contradictory things at once. If we cannot reconcile the contradictions, then we have no science. All the fundamental problems of modern science are as old as Western history itself. The problem began with the pursuit of objectivity. It required the rejection of the observer from the worldview. The senses and the mind were eliminated from science and replaced by instruments, hoping that this will give us objectivity. But instruments are not objective either. They are just like the senses. Then science tried to reduce language to objectivity by giving each word only one meaning. It was believed that if we can give precise definitions in mathematics, then mathematics will be the proper language for describing nature objectively. But the fact is that language also can never be objective because each word has multiple meanings, each of which is necessary, and all of them are collectively sufficient. Thus, the problem of objectivity in science became a problem of language, and the problem of language is the problem of objectivity. We cannot separate the problems of objectivity and language. All these problems then lead to multiple dualisms, incompleteness, and any attempt to overcome the incompleteness then leads to a contradiction. Thus, the entire enterprise of Western thinking, rooted in objectification of reality through science, logic, and mathematics, has completely failed. This failure is hidden from the eyes of most people by the use of dualisms. A dualism is a contradiction, but when a dualism is normalized, then contradictions are normalized. Every subject is riddled with dualisms. In this video, we have talked about 6 dualisms in physics. By their combination, infinite other dualisms can be produced. Western thinking has normalized dualisms and hidden all the problems by such normalization. But they appear again and again in the form of contradictions between theories because they are using different sides of the dualism. As time passes by, newer and newer dualisms are created. The issue gets so muddled with numerous dualisms that nobody has the capacity or the inclination to analyze the problem, and science takes advantage of this confusion to make false claims about progress. The fact is that there has been no progress in Western thinking for the last thousands of years. But some new phenomena have been discovered, although their explanations are false. Those new phenomena are used to build technology, get power, and then push the false explanation by fiat. The phenomena are correct and the explanations are false. The explanation constructs a physical picture of reality devoid of meaning and purpose. The physical picture depersonalizes reality and converts everything into material objects. This objectification is not the truth, and yet, because alternative explanations of phenomena are not permitted in science, or an alternative explanation is called pseudoscience, therefore, false explanations are taken as the truth. There are so many inconsistencies in the scientific narrative that we have to conclude that there are many falsehoods. The entire edifice of Western science, rooted in objectification and mathematization, is a falsehood. That falsehood is detected by the inconsistencies in the scientific narrative. But detecting the inconsistencies to detect a falsehood requires much effort. Most people are not interested in that effort. Therefore, knowing the truth also becomes a choice. Truth cannot be forced. There is always a choice between the uncomfortable truth and the comfortable falsehoods.